The device you have at home can consume more energy than all your other appliances combined. A single air conditioner running for 8 hours daily can increase your electricity bill by more than 50%. In this video, we'll tell you about the fascinating world of technology that revolutionized human comfort and understand why it requires so much energy to function. Air conditioning is one of the inventions that has most impacted our quality of life in the last century. Think about tropical and desert regions that now house modern megalopolises. Without this technology, cities like Dubai, Singapore, or Phoenix would never have developed as we see today. Let's discover how this machine manages to create an oasis of freshness amid intense heat and why it demands so much energy. To begin, we need to understand a basic principle of thermal physics. Heat always flows naturally from hotter to colder environments. Never the opposite. When we turn on the air conditioner, we are forcing heat to follow the path opposite to natural, removing it from inside an environment and throwing it outside, where it is usually already hotter. This process of moving heat against its natural flow requires a lot of energy. The heart of the air conditioning system is a cycle known as vapor compression. This cycle uses a special refrigerant substance, which has a fascinating property: the ability to change easily between liquid and gaseous states at temperatures close to our everyday environment. This substance is the key to the entire operation of the device. The refrigerant substance continuously circulates through a closed circuit of tubes inside the air conditioner. During this journey, it passes through 4 main components: the evaporator, the compressor, the condenser, and the expansion valve. Each of these elements plays a crucial role in the refrigeration process. Let's follow the journey of the refrigerant substance to understand how the system works. We start with the evaporator, located in the internal unit of the device, the one that stays inside the environment we want to cool. Here, the refrigerant substance is at low pressure and absorbs heat from the room air, evaporating. When air passes through these cold evaporator coils, it loses heat and its humidity condenses, coming out cooler and drier to the environment. After absorbing heat in the evaporator, the refrigerant substance, now in gaseous state, goes to the compressor. This is the part that consumes the most energy in the entire system. The compressor, as the name suggests, compresses the refrigerant gas, drastically increasing its pressure and consequently its temperature. This compression is necessary so that the refrigerant substance can later release the heat it absorbed from the internal environment. With the high pressure generated by the compressor, the superheated refrigerant substance proceeds to the condenser, located in the external unit of the device. In the condenser, the refrigerant substance releases the heat absorbed from the internal environment, plus the additional heat generated by compression to the outside air. During this process, the refrigerant substance returns to the liquid state, still under high pressure. Finally, the liquid and pressurized refrigerant substance passes through the expansion valve, where it undergoes a sudden drop in pressure. This decompression causes intense cooling of the liquid, which returns to the evaporator to restart the cycle. And so continuously, heat is removed from the internal environment and released into the external environment. This cycle is present not only in air conditioning devices, but also in refrigerators, freezers, and heat pumps. The basic difference is in the application and adjustments of the system. An ingenious principle that we use daily without noticing its complexity. But now we come to the central question: why does this process consume so much energy? The answer lies mainly in the compressor. To compress the refrigerant gas, the compressor needs to perform considerable mechanical work, and this demands a lot of electrical energy. In simple terms, we are using energy to force heat to flow in the opposite direction to natural, from cold to hot. To illustrate with a practical example, a typical air conditioner of 12,000 BTUs consumes about 1,100 watts per hour of operation. This is equivalent to keeping 10 ceiling fans running simultaneously, or approximately 2060 watt LED lamps. In a month of moderate use, just this device can represent a third or more of the total energy consumption of a residence. Besides the compressor, other factors contribute to the high energy consumption of air conditioning. The fans that move air through the coils also consume energy. The control systems, although less significant, add to the total consumption. On very hot days, the system needs to work even more intensely, raising energy expenditure. Few people know that air conditioning efficiency is also strongly affected by installation and maintenance. A poorly installed device with leaks in the cooling system or dirty filters can consume up to 30% more energy to produce the same cooling effect. Lack of regular maintenance not only increases energy consumption, but also reduces the equipment's lifespan. The architecture of the environment also directly influences energy consumption. Environments with inadequate thermal insulation, such as simple windows without sun protection or walls without insulation, allow constant entry of external heat. This forces the air conditioner to work continuously to maintain the desired temperature, significantly increasing energy consumption. Another important factor is the correct sizing of the device for the environment. An undersized equipment will work constantly at the limit, unable to reach the desired temperature and consuming more energy. An oversized device will turn on and off frequently, a process known as short cycling, which also increases consumption and prematurely wears out the compressor. Speaking of temperature, each degree less in the thermostat setting represents a significant increase in energy consumption. Experts recommend configuring the device for temperatures between 73 and 77 degrees Fahrenheit, which provide adequate thermal comfort with lower energy expenditure. Reducing the temperature to 68 degrees, for example, can increase consumption by up to 10% for each degree less. The good news is that technology has advanced rapidly in this area. Modern air conditioning systems with inverter technology constantly adjust the compressor speed according to the cooling need, instead of simply turning on and off like conventional models. This results in energy savings of up to 40% compared to older models. Number 1. Devices with the highest energy rating are up to 30% more efficient than models with lower ratings. Number 2. Keeping windows and doors closed during air conditioner use reduces consumption by up to 20%. Number 3. Regular filter cleaning can improve efficiency by up to 15%. Number 4. Using the timer to turn off the device during the early morning, when the outside temperature has already dropped, saves approximately 8 hours of daily operation. Number 5. Installing solar films on windows can reduce heat entry by up to 70%, decreasing the thermal load for the air conditioner. An interesting curiosity about cooling systems is their historical evolution. The first refrigerant substances used were compounds such as ammonia, sulfur dioxide, and chloromethane, which were toxic and dangerous. Later, chlorofluorocarbons, known as CFCs, were developed, which solved the toxicity problem but caused another, destruction of the ozone layer. Today, we use safer refrigerant substances for the environment, but we are still looking for perfect alternatives. It is worth noting that the environmental impact of air conditioning systems goes beyond energy consumption. The massive use of these devices creates a vicious circle in densely populated urban areas. The heat expelled by the external units raises the temperature in the streets, creating so-called urban heat islands. This temperature increase causes people to use air conditioning even more, which expels more heat outside, intensifying the problem. On a global scale, the exponential growth in air conditioning use represents a significant challenge for greenhouse gas emission reduction goals. It is estimated that by 2050, the number of air conditioners in the world could triple, reaching more than 5 billion units. Without significant improvements in energy efficiency in the global energy matrix, this could represent a substantial increase in carbon emissions. Beyond direct energy consumption, another often neglected aspect is the energy cost of manufacturing, transporting, and disposing of these devices. The so-called embedded or incorporated energy includes all the resources needed to produce the equipment, from raw material extraction to final assembly. Some studies suggest that this indirect energy cost may represent up to 40% of the total environmental impact of an air conditioner throughout its useful life. However, in an increasingly hot world due to climate change, air conditioning is not just a matter of comfort, but also of public health. During extreme heat waves, which are becoming more frequent and intense, access to cooling can literally save lives, especially for the elderly and people with pre-existing health conditions. This is a complex paradox. We need cooling to deal with global warming, but the massive use of air conditioning contributes to the same warming. The solution to this dilemma necessarily involves multiple fronts. First, the development of increasingly efficient technologies capable of providing the same thermal comfort with lower energy consumption. Second, the adoption of construction and urbanism practices that naturally reduce the need for artificial cooling, such as green roofs, shaded facades, and urban planning that favors air circulation. Third, the transition to renewable energy matrices, reducing the environmental impact of the energy consumed by the devices. There are also promising alternatives under development. District cooling systems, which centralize the production of chilled water for multiple buildings, can be up to 40% more efficient than individual devices. Adsorption or absorption cooling technologies, which use residual heat or solar energy instead of electricity for the compression process, also show great potential for reducing energy consumption. For those seeking immediate solutions to reduce air conditioning consumption, some simple strategies can make a big difference. The combined use with ceiling fans allows increasing the thermostat temperature by up to 7 degrees without loss of thermal comfort, as the air movement creates a sensation of lower temperature. The installation of awnings or external blinds can block solar radiation before it penetrates through windows, significantly reducing the thermal load. Another effective approach is zoned cooling, concentrating air conditioning use only in effectively occupied environments instead of cooling the entire residence or office. Modern systems allow this sectorized control, optimizing energy consumption according to the real needs of each space. The future of cooling involves intelligent integration with other systems. Connected devices can optimize their operation based on weather forecasts, learn environment occupation patterns, and automatically adjust to maximize energy efficiency. Integration with photovoltaic solar generation systems also presents great potential, allowing the highest energy consumption to coincide with periods of highest solar generation. Finally, although air conditioning is one of the largest energy consumers in residential and commercial environments, its importance for human comfort and productivity is undeniable. The challenge is to continue enjoying this benefit while working to minimize its environmental impact, whether through technological innovations, changes in consumption habits, or transformations in how we build and inhabit our spaces. If you value the comfort that air conditioning provides but worry about energy consumption, act now. Investing in a more efficient model, performing regular maintenance, and adopting intelligent usage practices will not only reduce your electricity bill, but also contribute to a more sustainable future. Don't wait for the next energy bill to arrive to take action. The planet and your wallet will thank you.